Every map we draw of the universe, from the orbits of our local planets to the distant cosmic horizon, relies on two highly successful theoretical frameworks. First, general relativity. A century ago, Albert Einstein redefined gravity as the physical warping of space and time. Second, the Lambda-CDM model. Building on decades of telescopic observations, this framework charts the expansion of the universe and identifies the distinct components required to build it. Together, these frameworks provide the mathematical language to chart macroscopic reality with a level of precision that earlier generations could barely imagine. General relativity captures the bending of starlight around massive galaxies, the slowing of time near heavy objects, and the gravitational collapse of massive stars into black holes. In 2015, massive concrete detectors like this one captured the ripples of two colliding black holes, confirming a complex prediction made 100 years earlier. Meanwhile, Lambda-CDM matches the ancient glow of radiation left over from the Big Bang and plots the giant sound waves frozen into the distribution of modern galaxies. These frameworks describe exactly what the universe does, but documenting the motion of galaxies leaves the fundamental causes a mystery. Classical relativity operates on smooth, continuous geometry, which becomes conceptually incompatible with the chaotic, unpredictable mechanics of the quantum realm. When physicists attempt to calculate the density of a singularity, whether inside a black hole or at the beginning of the Big Bang, the mathematics produce infinities. The model effectively breaks. We know from the thermodynamics of black holes that space must possess a microscopic informational structure. General relativity, however, possesses no variables to describe it. It treats the strength of gravity as an arbitrary implant. It dictates how geometry behaves without explaining why geometry exists as a fundamental feature of reality. Lambda-CDM requires unknown placeholders, dark energy and dark matter. Yet calculating theoretical vacuum energy yields a figure vastly larger than the dark energy observed. We also face a coincidence, occupying the specific cosmic epoch where matter and dark energy densities are comparable. This plot shows the statistical tension in modern cosmological parameters. Observational data from the early universe is increasingly at odds with our measurements of how fast late-time cosmic structures are expanding. The Lambda-CDM model successfully coordinates vast sets of observational data, but its reliance on dark placeholders leaves the underlying physics of the universe unresolved. History provides a clear precedent. Isaac Newton's mathematics perfectly calculated the orbits of the planets for centuries, despite offering no mechanism for how gravity actually crossed the vacuum of space. Eventually, Newtonian physics was enveloped by general relativity, which provided a new geometric explanation for gravity as the curvature of spacetime. Today, general relativity and the Lambda-CDM model occupy that same position. They are accurate surface descriptions waiting for their own larger theoretical envelope. Incomplete theories remain functional within their specific domains of validity, allowing us to accurately navigate the cosmos. Any future foundational theory must pass strict requirements. First, it must recover the mathematics of general relativity and Lambda-CDM in the regimes where they currently work. Second, it must resolve their foundational assumptions by unifying gravity with the quantum realm and explaining the nature of the dark sector. Third, the new theory must make clear and falsifiable predictions that can be tested against future observations. The question is not whether general relativity and Lambda-CDM are successful. They are. The question is whether their success is the final story, or the visible surface of a deeper layer of physics.